Hi everyone, welcome to the third and final video in our coverage of section 4.1. In part 1, we introduced the concept of optimization as a part of our everyday life. In part 2, we discussed various terms and concepts that will be valuable in this video. In this part, we will discuss mathematical optimization problems, specifically what they are and how to approach them. Then we will discuss a couple major theorems. The first will tell us when an optimization problem is guaranteed to have a solution. This theorem is known as the extreme value theorem. The second theorem will help us establish an algorithm for approaching optimization problems. At the end of the video, we will go through 3 examples. These examples should help us understand the method we present in this video, as well as help us review how to find critical points. So the first question is, what do I mean by an optimization problem in this class? As we discussed in part 1, real-life optimization problems generally consist of 1 or 2 things. The first one is some quantity we want to optimize. For example, you may want to minimize your drive time on your way to work. Another example would be trying to maximize your income when you get a new job. Sometimes an optimization problem also came with a constraint. For example, there are only 24 hours in a day. As we saw, these problems can be very difficult. Since it's generally a good idea to learn to juggle balls before you try to juggle chainsaws, we're going to break down these problems into their essential components. For us, a function is going to play the role of the quantity we want to maximize or minimize. Our constraint will be the domain we choose for our function. Let's recall these 2 non-examples we saw in the last part. We saw that the first graph of y equals 1 over x does not attain an absolute maximum on its domain 0 to infinity. This is due to the fact it has a vertical asymptote. The other example was the line y equals x, which doesn't attain its maximum value on the domain we prescribed here, the open interval from 0 to 3. So what can we do to guarantee that these functions take both their absolute maximum and absolute minimum on the domain we have? It seemed that the functions failed to attain their maximum and minimum values because the endpoints of the interval were missing. And it turns out our first theorem says exactly that, the theorem known as the extreme value theorem. It says that any continuous function on a closed interval must attain its maximum and minimum value. At first, this theorem may not seem like much, but it's actually very powerful. These types of theorems are known as existence theorems. Notice that by itself, this theorem tells us nothing about where that maximum and where that minimum value are attained. But in reality, the majority of us will generally use computers to try to maximize or minimize whatever model we are using. What this theorem says is that there actually is a maximum and minimum, which means there's something for the computer to find. So now let's revisit our counterexamples. In both cases, we'll change the domains so that they are closed intervals. Notice the graph of 1 over x is now restricted to the interval 1 to 2. This is highlighted by the red segment seen in the graph on the left. Because of this restriction, the domain avoids the vertical asymptote completely, and now the function 1 over x attains both its absolute maximum and minimum values on the new domain. Similarly, when we add the endpoints to the domain of y equals f of x, the function attains both its absolute maximum and minimum values on the new domain. So now the next question is, how do we find the absolute maximum and minimum value? Luckily, we spent a lot of time thinking about it in part 2. To address this question, we have this theorem below that basically summarizes a big chunk of the last video. In short, it says the only places an absolute maximum or an absolute minimum can occur: the endpoints of the domain or critical points of f. Another benefit of this theorem is that it reduces the amount of work we need to do to find the absolute maximum and minimum value for continuous functions on intervals that are closed and bounded. So here is a process by which we can find the absolute maximum and minimum values of a continuous function on a closed interval. The first step is to find all the critical points of f in the domain that's given. Then you evaluate f at all those critical points. Next, you evaluate f at the endpoints of your interval. At that point, you have a list of numbers. The largest of those numbers is the absolute maximum value. The smallest of those numbers is the absolute minimum value. For the remainder of this video, we are going to work through 3 different examples. I recommend each of you pause the video and try the exercises by yourself before watching the solution. Hopefully, you've all taken the opportunity to try this problem on your own. Based on our previous theorem, we know we should start by finding the critical points of f. Critical points are related to the derivative of the function, so let's start by computing that. Great. We know critical points come in 2 flavors. The first one happens when f prime is equal to 0. So let's set f prime equal to 0 and solve. The second kind of critical point occurs when f prime is undefined. In this case, since f is a polynomial, so is f prime. Thus, f prime is always defined. So now we will plug in the x values of the critical points and the endpoints. We see that the largest output is 27 and the smallest is -1. Thus, we know f has an absolute max at 2 and its absolute maximum value is 27. Similarly, it has an absolute min at 0 and its absolute minimum value is -1. Great, now that we've seen how the method works, let's try a slightly trickier problem. Again, I advise everyone to pause the video here and attempt this problem on your own before seeing the solution. Let's go through this example a little faster. Pay attention to the fact that the big steps are roughly the same. I'll slow down to point out the major difference between this example and the last. I recommend everyone take advantage of the fact that this is a video and pause when they need more time. Okay, here we go. First we take the derivative. Then we find the first type of critical point. That happens when f prime is equal to 0. So we set it equal to 0 and solve. Here is where we see the major difference between this example and the last. Notice that the critical point at -3 is not in the domain 0 to 4, so we have to throw it out. Now we look for critical points when f prime doesn't exist. But like before, f prime is a polynomial, so it always exists. Thus, there is no critical point of this type. So now we plug in the values of the critical points between 0 and 4, and we plug in 0 and 4 because they are the endpoints. Now we see that the absolute maximum value is 64, and it happens at x equals 3, and the minimum value is 10, which happens at x equals 0. Alright, this will be our third and final example. Try to see if you can figure out what makes this one trickier than the last example. You're probably tired of me saying this, but you should pause the video and try this problem before going on to the solution. Alright, we're going to go through this one even faster than the last one. Like before, I'll slow down to point out the major difference between this one and the other 2 examples. So let's start. We take the derivative. Then we look for the first kind of critical point. That happens when f prime is equal to 0. So we set it equal to 0 and solve for x. Notice that f prime has a square root of x in the denominator. That means the derivative won't exist when x equals 0. Hence, we have one of the second types of critical points this time. So now, just like before, we'll plug in the x values of our critical points and endpoints. Compare the outputs, and we see that x has an absolute maximum of 2 at x equals 4, and an absolute minimum of -1/4 at x equals 1/4. This concludes our study of section 4.1. Thanks for sticking through this with me. I hope you're not too tired of my voice by now. Before I go, I'd like to thank Ashley Kang and Professor Amber Rosen for all the help they gave me in making these videos. See y'all in the next video.